quiet. All right, today we're going to go over chapter 19. I'll do 19.1. We're going to talk about interference. So we'll do interference with double slit experiments. We'll calculate interference with thin film. We'll describe coherent light and talk about constructive and destructive interference. So the easiest one first, different types of light. There are three main different types of light, and we're not talking about color here. We're talking about the light itself. The one that we're most used to is incoherent light. This is like white light. It has many, many different colors in it, so it has many different wavelengths in it. So incoherent light is a mess of different wavelengths of light. Yes?
What about like when the light starts to fade?
Starts to flicker? Well, the light itself, I was told this once, actually does flicker. It just flickers faster than what our eyes can detect it. And if it doesn't get enough power, it will flicker slower so we can actually detect that flicker.
So whenever it changes color, it's just because...
Yeah, it's getting a different amount of power. And that different power can actually change the color of the...
Oh, is that why you see bulbs have buzz?
Yeah. Mm-hmm. Yeah, they flicker faster than we can detect it.
Wow.
That's because electrons are going through it. Now, that's something that I was told that I don't really know that much about light bulbs themselves. All right, the next type of light is coherent light. So if incoherent light is many wavelengths, coherent light must be less, right? Coherent light is more than one wavelength. It's wavelengths that all work together. So remember when we were doing sound and we had harmonics? If you play two harmonics together, they sound pleasant together. And that's because the wavelengths all line up. So if you were looking at like the first harmonic in a tube, it would look like this. If you're looking at the second harmonic in the tube, it looks like this. But the wavelengths fit in the tube evenly. You don't have any partial wavelengths. So if this was the first harmonic at 100 hertz, this would be the second harmonic at 200 hertz. So they're ratios of each other. Coherent light is like that. It's a couple of different wavelengths, or many different wavelengths, but they're all harmonics of each other, if you will. So if you had the third one, you'd have like that, and it would all fit. You're not going to have any 2/3 of a wavelength or anything. They're all going to work together. They're all going to fit in your tube or your length that you're talking about. So this is coherent light. Many wavelengths, but they all have ratios, equal ratios of each other. And the last one is monochromatic. This is one single wavelength of light. 480 nanometers, that's it. 720 nanometers, that's it. Just one wavelength, one color, monochromatic. All right, in that video today, you saw a demonstration of Thomas Young's double slit experiment. So in that box, they had two really tiny slits, and they used the sunlight to go through those two slits. And instead of seeing either one blob of light or two blobs of light, they saw an interference pattern. They saw this one right here. So you can see we have this white band in the middle. And then you can see this white band over here, and then it kind of disappears, it fades. You've got a red, blue, green line right here, and another red, blue, green line right here. It repeats itself. Remember that white light is made up of red, green, and blue light, and white light, red, blue, and green light all have their own wavelength. So if we put red light through the slit, the two slits, we end up with this sort of pattern, with red and black and red and black. Now the red part could be constructive interference, where you get a bright line, or a louder sound if we were talking about sound. And the dark lines are where there's destructive interference. You get quiet, right? But with light, not sound. And then here's blue light. It has a shorter wavelength, so this actual fringes, that's what these are called, fringes, are smaller. So you get a little tiny black line and a smaller blue line. So constructive, destructive, constructive, destructive. If you were also to look at the green light, you get the same sort of thing. It would be somewhere in between the blue and the green. And if you layered them all on top of each other, this is the pattern you get. Because when you add red, blue, and green together, you get white light. So each of this white light, since they refract at different angles, they're going to spread out and you're going to get this rainbow effect. And this rainbow effect is called an interference pattern. And I have this lovely little picture down here at the bottom. You can see a source, and it hits two slits, and it follows Huygens principles. Remember what we talked about last week? Imagine sound. Imagine you're out in the hall and you're listening to me talk. It sounds like the door is the source of the sound. You know I'm making the noise, but the noise is coming directly from the door. You can't tell if I'm on the right side of the room or the left side of the room. All you hear is the noise from the door. As soon as you poke your head in here, though, you can be like, oh, she's standing on the right side of the classroom and not the left. So that spot when you're standing out in the hall and it sounds like it's coming from the door, that's Huygens' principle. The sound comes up to the door and then it creates, the door itself becomes the source and the waves spread out from there. The same thing happens with light. But because light is so tiny, its wavelength is really, really, really small, the slits have to be really, really small. Otherwise, it'll just pass through there without doing any of this diffraction. So what happens is we have our source, it comes up to these two slits, it follows Huygens' principle, and it starts to spread out from there, diffraction, bend around these corners, and these waves can interact with each other. So you end up with constructive interference, where they perfectly overlap, and you get a bright light, and destructive interference, where they're perfectly out of phase, and you end up with a dark fringe. So you have bright fringes and dark fringes. Now you saw this when they did it with the two balls on top of the water. They were making two wave patterns, right, outwards. And if you looked a little bit further away, you could see where there were waves and then where there were no waves. So it looked like this. That's terrible. I'm sorry. So the sources were here and here, and this part canceled, and the wave part didn't cancel. So they got waves, so this would be the bright part, this would be the dark part, and that would be the bright part, and that would be the dark part, and that would be the bright part. You okay?
No.
You can sit in the hall if you want. Okay. All right, here's a three-dimensional view, since light and sound are 3 dimensions. We have just a nice wave. Now you can think of this as being really far away from the source because it's practically flat, right? So just look at like the curve on this. When it first comes out, it's very curved. As it goes further out, it's not quite as curved. So if you're on like a really huge circle, it looks flat, like the surface of the Earth looks flat from our point of view because it's really big. So that's kind of like this area. It goes through a single slit and it diffracts, right? It's going to spread out from that source. And then it hits 2 slits and it's going to diffract from both of those. And these waves are going to interact with each other. So where they cross, you're going to get a really bright line or a very large sound. Here is more of a wave view of it. We have our 2 slits, and at some point on our screen, they come together and they're in phase. So see where they land both on top of each other like that on the top? These 2 things are in phase, so they add together and become a bright spot or a loud sound if this was sound. Now if we move that a little bit, we find a spot where one lands on the top and one lands on the bottom. You get out of phase, destructive interference, and you cancel each other out. So you either have no sound at this point, or very low sound, or you have no light at this point. That's that dark band. So let's do some calculations with this stuff. Here's our equation. And I gave you a little picture so you can figure out where all those letters are going to go. So I always thought this MXW over L kind of looks like Maxwell. Help you remember it a little bit maybe. This is lambda. It's the wavelength of light. So your wavelength of light is usually between 700 and 400 nanometers. So you need to make sure you convert from nanometers to meters. All this stuff should be in meters when you put the calculation in. Your M is something new. It is a number, a whole number. And it's going to be your number fringe. So looking at this little picture right here, this fringe right here would be 0. These two fringes would be 1. They're first order fringes. These dark bands would be first order fringes as well, because the center is 0 and you get 1, and then these would be the second order fringe. So you just move your way outwards.
The W, is it from the center of the slit or from the edge of the slit?
It's from the center of the slit, except that they're really small. They're like millimeters apart, so it's kind of hard to tell exactly. But yeah.
Well, will that
from the
usually
center.
be given?
Yeah.
Okay.
I mean, or calculate. It's not something you're going to have to measure. All right, the L is probably the easiest. It's the distance between where your light source is and where your screen is. That one is centimeters, meters. Again, always convert to meters. Your W is the width of the slits, usually between millimeters and centimeters. Your X, usually in millimeters or centimeters as well. It's going to be whatever fringe you picked. So if it was the first order fringe like this one, be from the center fringe to the middle of the first order fringe. Or if it was like the dark band and it said the dark second order fringe, then it would be from the center to the second one up there. If it said the second order dark fringe, so second order dark one, you're looking at the darks. From the center, this would be first order, this would be second order. And you'd measure from the center to the center of this one. Again, make sure you convert all these things into meters so that they cancel. Now this is usually what you'd be looking for is the wavelength of light. Because if you set up an experiment and you had a laser, you could probably measure the width, you could probably measure the length. You'd be able to see the pattern on the screen, you could probably measure the distance between the fringes. So this stuff would all be known. So this is usually what you'd be calculating. Now, given all the other numbers, you can always find the one that's missing. But if you were looking at it in a lab, that's where it would
The
be.
M is there just to remind you to keep in meters?
No, the M is the fringe number.
Okay.
This is the center, so this is 0. This would be the first dark band. This would be the first red band. This would be the second dark band. So it's whatever fringe it is. Usually it'll say like the second order fringe. Or
If it's the second order, you put it through there?
Mhm. I mean, it depends on the wavelength and the brightness of the light. The brighter it is, the further out it'll go. It could be like, I've seen them as high as 12 legends. When I've done it on the board, not here, when I was in optics lab in college, we had 20 fringes or something like that. And it made a pattern like this on the wall. And they were really close together. Well, it was hard to count. All right. Here's some more pictures. So red is wider than blue because red has a larger wavelength. So you get wide bands. Your blue ones are skinnier because they're smaller. And if you overlaid all of these, you end up with this one right here. Where the red, green, and blue line up, you're going to get the white spaces. Red is always bigger than blue. Okay, so thin film interference. I bet you've wondered why bubbles look so pretty. No? Why are they all rainbowy?
You don't just question.
Why is the gas on top of a puddle all shiny and rainbowy?
Gas on top of these puddles? Yeah, like in a parking lot. When
In the
it's
parking lot,
shiny.
or oil. The reason is because of interference. Now, sometimes that oil on top of the puddle is moving, so it actually looks like it's almost swirling around. And that's because it's changing thickness. As the oil moves, the interference of the light changes. So if you look at my little picture here, we have a nice little thin part of the film. So what happens is light comes in, it reflects off the top of the puddle, of the oil. It goes through the oil and it reflects off the water underneath. So you end up with two different light rays. One could be red and one could be blue. So you're going to end up with a different color when it reaches your eye. Whereas if it's thicker, it's going to be offset even a little bit more. So it's going to be a different color. So you end up with this striped or rainbowy type pattern like this bubble up here. Different thicknesses are going to cause different colors. And wherever you're standing at, it's going to make that little rainbow effect because you're seeing the white light rays all spread out. So this is thin film interference. In this case, it's not the separation of white light, it's more the interference pattern of those waves. Which an interference pattern kind of separates them, but not quite the same. All right, here's the really tricky equations for this stuff. This is in your book at 521. It took me about an hour to decode it. It was not fun, I can tell you that. But this is how I interpreted it. So you have two main equations, and depending on what it's asking and what the puddle setup is, or the bubble, and I'll teach you what all this stuff means. So just write it down for now, and then we're going to go through it. This is the hardest part of the chapter.
This is the last part of it.
No. Well, that's for today, yes. I'm sorry you're so tired. In my class.
It's just today. Like, I'm usually tired of things. I'm taking the liquor on Fridays. I was doing the same as subtle times, wavelengths over time. So is that time wavelength over film, or is that just
Times. Okay, I'm going to walk through this. T is the thickness of your film. So if you think about the back of the CD, it's really shiny and rainbowy. It's going to have some sort of film protective cover over top of it that the computer etches its laser into or whatever, with these little dots and stuff. So this is the thickness of that film. It's the thickness of the oil on top of the puddle. It's the thickness of the bubble. M is your order fringe. Is it the first order, second order, third order? How far away is it from the center? Is it the first band? Is it the second band? So it's going to be a whole number. It says plus 1/2, and we have wavelength of the light. If it's red light, if it's white light, if it's white light, it's going to be many wavelengths, so they won't give you that. Then N is a new variable for us. It's the index of refraction. Each object has its own index of refraction. For instance, air is 1, water is 1.33, diamond's 2.42. So it has its own. You have to look it up. It'll be in your book. There's a big chart.
And the higher the number, the more reflective it is?
The higher the number, the denser it is. Sort of. It's a refraction property. It's not reflection. And then the same thing in this equation. We have 2 times the thickness is equal to the order fringe times the wavelength of light over its index. Now, if you notice, underneath each of these equations has a different setup. So it says constructive and destructive. Let's look at those first. That's the easiest to tell apart.
What does it mean by inverted?
We'll talk about it in a second.
Oh, okay.
All right, we have constructive. If it asks for constructive, they're looking for the bright fringe, the color. So this would be the light color fringe, the white band, something like that. If it says destructive, this is the dark band. This is where there is no light. So destructive means it's canceling, constructive means it's adding together. So here you should see a color and here you won't see a color. It'll be made up of stripes, of dark and white bands, or dark and red, or dark and blue. So the blue would be the color and the dark would be the destructive part. So that's the constructive and destructive. So your question will ask you where the bright band is or the dark band is. It says dark band, use destructive. It says bright band, see constructive. Now let's look at the inverted part. This is the trickier part. You have to draw it. There really is no other way. So let's look at a bubble. With a bubble, we have air, and then you have soap, and then you have air, right? And the bubble would, have air in the middle and then air on the outside. And the bubble is the soap part. So air has an index of 1, and soap, let's say, has an index of 1.3. Very close to water. So when the light comes in, it goes from a lower index to a higher index. It's going from 1 to 1.3. So it goes up from low to high. And then when it goes through from 1.3 to 1, it goes back to low. So it's dropping from 1.3 to 1. Now this sentence right here is very important. I want you to write this down. It says a wave is inverted when it goes from low index to high index. So that happens up here where we go from 1 to 1.3. So this one's inverted. But from here it goes from high to low, so it's not. So this only has one inversion. All right, so if it's one inverted, if the question says where is the bright band, then we'll use this equation. If the question says where is the dark band, then we'll use this question for this equation. Yes?
Is that how they're going to word it in every question, or are there going to be questions?
Something like that. Yeah, it'll either be dark band or light band.
So there won't be questions where they don't suggest it's another thing? Obviously suggest.
I don't think so. Okay, so let's look at one that has 0 or 2 inversions to it. All right, we have air, oil, and then water. Sitting under your car is leaking. Air's index will be 1. Let's say your oil is 1.2 and your water is 1.3. All right, so from air to oil, we go from low to high. Is this inverted? Yes. So inverted. Then it goes from high to, well, it goes from 1.2 to 1.3. So it goes from lower to higher. So it is inverted again. So this one has 2 inversions. See why it's better to draw them so you can kind of look at what's going on?
How do you know the numbers?
I just gave them numbers. I mean, I have them kind of memorized, but these ones you would look up in the book. Okay, so 2 inverted. So we're going to look at this part. If it's looking for a dark band, we'll use this equation. And if it's looking for a color band, then we'll be looking for this one.
And that would just be like any even numbers, or it only works?
Any even.
Okay.
Yeah.
And
It
then
won't ask you.
the other question I have, if it went to like air to soap to air to water and bounce back up, would that make it like 3?
Well, we'd have to look at it. I think it would make it 2 again.
Okay, so when it goes back up, it doesn't really matter?
Yeah, you're just looking on the way down.
Okay.
Yeah.
Okay.
Because if you had like soap again, or water, so air to, you're asking if this was water down here,
Yeah, because
1.3.
like, if it goes to water and it comes back up...
Because this would be one inversion, this would be from low to high again.
That would be 2, but then if
That
it
would
goes
be-
back up, it makes another...
No, just look it on the way down, because
Okay.
we're already taking care of the way up. Okay, so here is, are we finished with this slide? Okay. Here is the picture You can see the light reflecting off the top of the oil or the film, and it also goes through and it reflects off the bottom, the water, or the glass, or the mirror, or whatever's down there. Usually this is the third order band. If it doesn't tell you, you can assume first order.
I meant like what order of items.
Yeah. Mm-hmm. It'll say like a gas kettle, the gas oil top of water, so you'll be able to do it.
Alright.
All right, so I have some clicker questions for you today. They're not very easy clicker questions to start out with. They get easier.
First time, I'll get them over.
Yeah, we start with the hard ones to get them out of the way.
I already got you